said, I work here at the group of condensed matter here in this building. And the work I'm going to present is titled Crossover Regime in a manganite-based resistive switching memory device. This has been the work of some people which are listed here. Basically, sorry. Okay. Thank you. Okay. So, as I was saying, this has been the work of some people. Ignacio Alposta, which is an undergrad student directed by Pablo and me. Ariel Kalstein, who is a PhD student here in the group. Nestor Hensi, who helped with the microfabrication of the electrodes in the thin films we got. And Pablo, who is the head of the group. So, I think you should be a little bit tired of this kind of introductions, so I will avoid it. Of course, resistive switching is divided in unipolar and bipolar. Usually unipolar is found in simple oxides or binary oxides, while complex oxides such as manganites display the bipolar behavior. The unipolar behavior is usually related to the creation and breaking of a conductive nanofilament connecting the two electrodes of the device, while bipolar resistive switching in complex oxides is related to the electrical drift of oxygen vacancies close to the oxide-metal interface. In this way, you can put or remove vacancies, and in this way, you can modulate the resistance of the interface. One thing that I would like to remark is that these two kinds of resistive switching mechanisms can be described or identified by plotting the resistance of the lower or the high resistance state as a function of the area of the electrodes. Sorry. If in the case of the interface effects, there is a clear correlation between the resistance and the area, while in the case of the filamentary effect, you expect no dependence. So, why we want to grow thin films? Of course, this is the form needed for applications. You can take advantage of the strain between the film and the substrate. You can also point to obtain finite size effects, surface effects. You can combine different materials in heterostructures or multilayers with improved functionalities. And in the case of thin films for resistive switching, the very good thing is that you can achieve electrical fields which are much higher than in the case of the ceramics millimetric samples that we have been dealing with in the past years. So we have started growing thin films about a year and a half ago, and we started in two lines. One line was the titanium dioxide spattered thin films that Nestor Hensi showed you a couple of hours ago before lunch, and the other line was the growth of thin films by pulsed laser deposition, and we grew thin films of the lanthanum calcium canonical manganite and also bismuth ferrite. We use a PLD facility available at the Faculty of Engineering of the University of Buenos Aires, and luckily we already started growing thin films with a new facility available here at the Tandar building, and we grew the first film last week. So from up to now, we use the Faculty of Engineering facility, but from now we will use our own facility. So we grew lanthanum calcium manganite on top of conductive silicon. In this way, we can use the substrate, the silicon, as bottom electrode. We use standard deposition conditions. The only parameter that we varied systematic way is the oxygen partial pressure during the growth. We did no annealing after the growth in order to quench the oxygen content of the films. We avoid annealing and we avoid modifying the oxygen content, so we wanted to see what was the effect of the oxygen content on the electrical properties of the film. These two XRD spectra, the black one is the one of the powder that we made the target with, and the other one is film, and we can see that every peak is in its place, and the film is polycrystalline without any texture. This is the same picture of the surface of the film, and we saw the presence of some particulate, which is not optimal, but in any case, we have been able to work and obtain some results. So this is the configuration we use for the electrical measurements. We measure in the transversal configuration, where the bottom electrode is the silicon, as I said, and we use different top electrodes. Here I will show the results we found using silver, prepared by just painting with silver paste on top of the oxide. And I will show also results with the copper top electrode that was prepared by spattering and miniaturized by means of optical standard lithography. The electrical protocol we use to characterize the film is depicted in this figure. We basically do a pulsed IV curve with some pulses of increasing amplitude, and then we reduce it, and then we go to the opposite polarity and we complete the loop. And between two pulses, we apply a small reading voltage that allow us to determine after each dynamic pulse, the remnant state. In this way, we obtain two different figures for each run, which are the pulsed IV curve, which is the dynamic measurement, and the so-called hysteresis switching loop, which is a remnant measurement. So these are typical IV curves for an LCMO film with silver electrodes. This is the dynamical IV curve. It is seen clearly the set and the reset events. The set and reset voltages were both between 3 and 4 volts. And the hysteresis switching loop displays clearly the high resistance and the low resistance level. One thing that it is worth pointing out is that the hysteresis switching loop is squared. It presents a squared shape. And this indicates that we may have only one active interface switching, while the other one remains ohmic, based on the plenty of results that appear in the literature saying that manganite silver commutes. It is reasonable to say that the resistive switching takes place at the silver oxide interface, while the oxide silicon interface remains ohmic or quasi-ohmic. What we did, and I forgot to say, is that we use a current complex for the set process. In this way, we limit the current that passes through the device when the set occurs, and then we prevent damage. What we did is we have varied systematically the current complex during the set process, and we studied the evolution of the low and high resistance levels. It is found in this figure that this is the evolution of their area high, and this is the evolution of their low, and we see that for low complexes, that is here, the high resistance level remains nearly constant, while the low resistance level decreases. At some point, the high resistance level starts also to decrease, and if we plot the ratio between both of them, which is a figure that says how good is the junction in terms of area high and area low window, we see that there is a maximum in the area high, area low ratio, and then it drops. The maximum value we obtained was about 1,000 for intermediate complex currencies. And the next step was to study the influence of the oxygen content of the films in the electrical properties. And for that, it is good to know it is good to quantify which is the oxygen deficiency of the films, which is directly correlated with the manganese valence. And to determine the manganese valence, we used XPS, and in particularly we focused on the manganese 3S level, which displays two peaks which are splitted, and it has been proposed in the literature that this splitting it has a magnetic origin. It has an origin on the intratomic magnetic exchange of manganese ions, and the amount of the splitting, this number, is directly correlated with the manganese valence. For that, we see that for a film grown at 0.35 millibars, the former manganese valence is 3+, and this indicates that the valence is close to the nominal one, and we may have no oxygen deficiency, but if we lower the pressure, we have a mixed valence state, which indicates that oxygen vacancies are created. If we replot the air high, air low ratio as a function of the compliant current for films grown at different oxygen pressures, we see that if we increase the oxygen content, the ratio clearly decreases. So this indicates and confirms that the oxygen content do play an important role in the electrical behavior of this kind of films. Next, we try to switch between low and high resistance by applying pulses. We found that if we use the simplest protocol, that is applying a positive voltage for set or a negative voltage for reset, the efficiency of this procedure is really low. It's only about 50 or 20%. So what we did is writing a kind of semi-intelligent protocol that determines if after applying the pulse the resistance has switched or not, and in case it has not switched, it insists. And it insists until the material switches. And this is in this way we have been able to switch many times. It's like 120 times, and then we stopped it. And here are the number of pulses necessary to switch every time in this figure and in this figure, and it can be seen that the set, which is the red one, this figure, seems to be easier to produce than the reset event. In any case, it is found that in this kind of samples, you cannot switch with just one single pulse, but you need a kind of smarter protocol in order to achieve a better efficiency in the switching. Then we moved to thin films with deposited copper electrodes. These electrodes are more controlled, have been deposited by sputtering and miniaturized by means of optical lithography, and we found that the effect is similar to the case of silver electrodes, but it's more clean and repetitive than in the other case. We also found different set and reset voltages. It has been found that the set voltage is systematically between 6 and 7 volts, while the reset voltage is between 2 and 3. And this is in contrast with the silver case, where we found 4 and -4 reset voltages in almost every case. And here you have this hysteresis switching loop, which is perfectly squared and display the two resistance values. We try to get some insight into the electrical conduction mechanism for this kind of samples, and this is a sample measured with a low complex current, and we found that if we plot in a log-log graph, this is the low current, so the high resistance and the low resistance. And checking in the literature what can be said about this, we believe that the high resistance mechanism may be related to a space charge limited current mechanism, while the high resistance level follows a quadratic law at a slope in log-log scale of about 2. What we did is increase the complex current and follow this slope to see how it evolves. And we found that for low complex currents, the slope is nearly 2, but then when we increase the complex current, then this slope changes to 1, which implies a nearly ohmic behavior. So this may indicate a change in the resistive switching mechanism, and indeed, if we see the dependence of the low resistance state as a function of the electrode area for low and high complex currents, we see that for the case of a complex current of 10 milliamperes, which is low, there is a clear dependence of the resistance as a function of the area, while if we go to higher complex currents, which is 110 in this case, the blue ones, there is roughly no dependence. So this indicates that we are seeing a crossover of the resistive switching mechanism, that for low complex currents it is related to an interface effect, probably associated to the movement of oxygen vacancies by action of the electrical fields, while for higher complex currents we propose a filamentary regime which is related to the diffusion of the top electrode through the oxide until the bottom electrode and the formation of a conductive filament. This is the plot of the area higher area low ratio as a function of the complex current set, and it presents a similar behavior that we observed with the silver electrodes, with a maximum well defined at about 50 or 60 milliamps. And then we asked ourselves if it is possible to delay the appearance of this peak or to avoid the formation of a filament which is appearing in this zone. And one option is to increase the film thickness. In this way we make the top electrode harder to achieve, to reach the bottom electrode. On the other hand, we decrease the electrical field across the film, so this may be could be helpful. And we repeated all these experiments, and we found that the ratio increases monotonically up to higher complex currents than in the case of the thinner film. This is a 250 nanometers film, and the previous one was a 100 nanometer film. So this seems to be consistent with the scenario we were thinking about. Then finally, what we did is irradiate with oxygen ions with this dose and this energy here at the Tandar accelerator, and compare the electrical behavior with respect to a non-irradiated film. And we found that both area high and area low shift to lower values at a fixed complex current, of course. Indeed, if we plot the evolution of the ratio and of the slope of the low resistance state, which are the green points, it seems to be that we have a more faster degradation in the case of the irradiated sample and a faster approach to a slope of 1 in the case of the irradiated samples also. So this indicates that the radiation damage could ease the appearance of the filamentary regime. So, as a conclusion, we have grown lanthanum calcium manganite thin films displaying resistive switching behavior. We have found a figure of area high, area low ratio of up to 3 orders of magnitude higher than those displayed by ceramic samples. We suggest a crossover from an interface-related resistive switching to a filamentary regime, depending on the set complex current, and we began to explore the electrical behavior after ions irradiation. Our perspective is to go further in the miniaturization of the devices, is to optimize the pulsing protocols to get a better electrical response, and to further explore the electrical response of these devices in hostile environments such as ion irradiation. And importantly, we are willing to model the observed behavior, and in this respect there is a poster of Federico Tesler, who is doing this kind of job. Okay, this is the acknowledgements, the funding, and thank you very much for your attention.
Thank you, Diego. We are open for questions.
You should, yeah. Please explain to me what's happening there. Is the current constant as you're sweeping the bias?
Sorry, this is, I think I didn't say, it's the hysteresis switching loop. It's the remnant state.
But for each voltage, the current is the same.
But we are applying a small reading voltage of 100 millivolts. It is not the dynamic IV curve.
It's Oh, this is the.
This is the remnant curve. Sorry if I didn't say it.
Yeah, okay. But the voltage is the voltage of the pulse, but the current is the current that you read the resistive
Yes,
set.
exactly. Yes.
I understand now.
Sorry for not being clear.
Diego, I have a doubt. I mean, when you apply the high compliance and you complete the filament, how you get back to the high resistance states? I do not understand. I mean,
It can be any of the mechanisms known for filamentary regimes. You can burn it by Joule effect, for example.
But in this way, you are not guaranteed that you are going to have bipolar. It could be
It
unipolar.
can, indeed.
But for bipolar, you need some, I mean...
Yeah, I know. Indeed, for low complexes, I checked that it is indeed bipolar.
Of course.
If you go to higher complexes, strange things start to appear. You can see set or reset with the wrong voltages. So this indicates that it may be unipolar, yes.
Okay.
I don't know if this answers your question.
Yeah, I do not understand the bipolar once the filament is completely formed because you have an ohmic
If you measure bipolar, you will see bipolar.
No, but I do not understand which is the mechanism behind because you don't have enough electric field to move nothing. I mean,
I think it's a filamentary regime associated to the migration of copper or silver ions or atoms on the oxide.
Okay.
Other questions, comments? Regina?
So you're using silicon as substrates. You're not having silicon oxide?
Sorry?
You're not having silicon oxide at the interface between your oxide and
It's
silicon?
just 2 nanometers.
2
You break
nanometers.
it very fast with a few volts. Yes.
And the CMO is P-conducting, isn't it?
Sorry?
It's P-conducting, the LCMO.
Be conducting.
P-conducting.
Oh, yes.
So why do you have then ohmic contact to the N-conducting silicon?
Yes, that's a good question. I don't know.
Okay.
Yes. Yeah.
So thank you very much.